Have you ever stopped to wonder what's really going on inside the devices you use every single day? Well, today, we're pulling back the curtain on computer architecture. Think of it as the secret blueprint that dictates how every laptop, phone, and tablet actually thinks.
So, let's start with a big question. What really makes one computer faster than another? It's not just about the brand name or that gigahertz number they print on the box. The real answer goes way deeper, right down to its core design, the architecture itself.
So here's our game plan. We're going to start with what a computer's blueprint is all about. Then we'll check out the original one-road system. That's the von Neumann design. After that, we'll see how it got a major upgrade with a two-lane expressway called the Harvard Architecture. We'll also uncover how modern computers get the best of both worlds. And finally, we'll see where these designs are hiding all around us.
All right, first up, let's understand the master plan. You can think of computer architecture just like the blueprint for a house. It doesn't just show you where the rooms are, right? It shows you how all the important stuff, the plumbing, the wiring, the hallways, all connects to make the whole house actually functional.
So breaking that down, it's the fundamental design that dictates how all of a computer's hardware components play together. And the most critical part is how the brain of the computer, the CPU, gets the two things it absolutely needs to function. Instructions, which is the what to do, and data, the stuff to do it with. This design, right here, is probably the single biggest factor that determines a machine's speed and efficiency.
Okay, let's dive into the first major design, the one that really kicked everything off, the von Neumann architecture. It's so elegant, so simple, and believe it or not, it's still the foundation for a ton of modern computing.
The key idea here is actually incredibly simple. It uses just one single shared memory space to hold everything, both the instructions and the data. I want you to imagine a kitchen where your recipe book and all your ingredients are stored in the exact same pantry. You can only go in and grab one thing at a time.
So because of that design, it works on a really simple repeating cycle. First, the CPU has to go fetch an instruction from that shared memory. Then, it has to decode it to figure out what it's supposed to do. And finally, it executes that command. It just does this over and over and over again, one step at a time, using that single pathway.
But this beautiful simplicity leads to a really big problem, what we call the von Neumann bottleneck. Because the instructions and the data have to travel on the same single road, or bus, as it's called, they can't move at the same time. Everything has to wait its turn, which creates a massive traffic jam, and seriously limits how fast the whole system can run.
So, how did engineers get around this traffic jam? Well, it's simple. They built a second road. And that brings us to our two-lane expressway, the Harvard Architecture.
The solution here is just brilliant. It creates totally separate memories and separate pathways for instructions and for data. Now, what does this mean? It means the CPU can be fetching the next instruction from one road while it's still working with data from the other road. No more waiting in line. It's a huge performance boost.
And this table really shows the trade-offs perfectly, doesn't it? On one hand, you have von Neumann. Single memory, single bus. It's simpler, it's cheaper to make, but it's slower because of that bottleneck. On the other hand, you've got Harvard. Separate paths for everything. It's way faster, but it's also more complex and more expensive to actually build.
So that leads to a really interesting question. If the Harvard design is so much faster, why don't our super powerful modern PCs just use that for everything? It's worth thinking about that balance between raw performance, complexity, and of course, cost. Well, the answer to that question leads us right to the solution we use today. It's this really ingenious compromise that gives us the best parts of both designs. It's called the modified Harvard architecture.
So here's the clever part. Inside the CPU chip itself, it uses separate, dedicated paths for data and instructions. This is what we call caches. This gives it that blazing Harvard-like speed for whatever it's working on right now. But when it needs to talk to the computer's main storage, it connects to a single, shared memory, which keeps the overall design way simpler and cheaper, just like von Neumann.
So this is the crucial takeaway. This balanced approach is exactly why the modified Harvard architecture became the absolute gold standard. It gives us that amazing performance we want, but without the crazy cost and complexity of a pure Harvard system. And that makes it perfect for basically every device we use, from our phones to our PCs. All right, to wrap all this up, let's just take a quick tour and see where you can actually find these different blueprints out in the real world.
As you can see, that original super simple von Neumann design, it's still useful for some really basic systems where cost is everything.
The pure, high-speed Harvard architecture is the go-to for specialized chips like microcontrollers that just need to do one thing really, really fast. But for pretty much everything else, our PCs, our laptops, our smartphones, the balanced, efficient, modified Harvard architecture is king.
And that really leaves us with this one big idea. The next time you pick up any device, just remember that underneath it all, there's a fundamental blueprint that defines what it can do and how fast it can do it. Because at the end of the day, computer architecture is the backbone of how fast and smart a computer can be.